Bismillahirrahmanirrahim. Assalamu alaikum. Hello everyone. In this video I will share with you the solution of homework 1 assigned to my students, where it is required to understand the functionality of a given RLC circuit. The RLC stands for Relay Logic Control Circuit, and they are asked to draw the power circuit that controls the two motors and introduce any safety components needed to both the control and power circuits. Make use of the available lamp on the operator's panel to reflect possible faults, and upgrade the RLC to a control circuit involving a PLC device, such that they need to do the I/O mapping and draw the schematics and write a ladder diagram that do the same function as the RLC, and to explain it as well. So this is the given operator interface. Here we have a set of 4 push buttons. Here we have the start and stop push buttons, and those are assigned to start each motor individually, and they are assigned tags as M1 and M2 respectively, and those are the indication lamps. M1 is associated with the running status of the first motor, and the second lamp is M2 is associated with, or H2 is associated with the running status of the second motor, and this is the available fault lamp that the students need to utilize in order to reflect any kind of faults happening at the system level. So in order to understand the concept of relay logic control, this is an animation prepared for my students so that they understand the flow of the current. You can see here the line in blue, the line in yellow actually represents the current flow. As you can see here, we need to establish a closed path between L1 and the N, whether they are AC or DC, we don't care at this moment. So now here we have the symbols, IEC symbols of the push buttons and the normally open, normally closed contacts, and the lamps, indication lamps or signal lamps, they call it usually. Here we have this situation as the initial situation, and if we go to the next slide and the operator comes here and push the start button, now there is a closed path established, as you can see here, between L1 and N, comprising the stop and start push buttons and passing through the coil of the contact K1. And once K1 gets fully energized, now its associated contacts will actually flip their states, and they will establish a kind of alternative path, a parallel path that bypass the start push button, and the operator can now safely release his or her hand, such that there is no need to keep pressing the start push button. Now this is called self-latching circuit. Now the power is delivered and it is ready to be passed to the contactors responsible for running the motors, whether it is the first and or the second motor. So let's have the first scenario where the operator wishes to start the first motor based on a prescribed standard operating procedure, usually accompanied with the manufacturing processes. As you can see here, the operator presses H1 and there is a closed path passing through K2, and as a result, once K2 is fully energized, its associated contacts will flip, since they are normally opened here, and they will get closed. And you see here the associated contact of K2 was initially closed, and now since it is fully energized, it will get opened, and the indication lamp will be eliminated, and the operator can release now the push button. As a result, this will be reflected on the operator interface on the lamp, and as you can see here, it is turned on, and as a result, the motor will hopefully start. We don't know that yet for sure, since we need another level of feedback, that since maybe the current flowing through the motor terminals, or maybe a speed sensor, so that we can tell for sure or will be certain about the status of the motor, whether it is running or not. But for now, this is a kind of visual feedback where the operator can tell that the motor should be running. Now, if the operator accidentally pushes H2, which is not, which he or she are not entitled to do so. So trying to push H2 will have no effect on the circuit, since we have already here a protection or a kind of electrical interlock between the two motors. So since motor 1 is running, the motor 2 is prohibited from running at the same time. So in order to stop the operation, we need to restart it from the beginning, and we can do so by pressing only the stop push button. So once the operator pushes the stop push button, now the electricity will be interrupted and there is no current flow through any component available in this RLC circuit, and we will come back again to our initial state as shown here. Now this will be reflected on the operator interface as shown here. There will be no lamp or a signal lamp that is turned on. Now if we start the cycle another time by pressing the start push button, and now we are willing to start the second motor instead. Now we are repeating the same story here, and now the operator pushes H2, willing to start motor 2, and once K3 coil is fully energized, the associated contacts will flip their states. As you can see here, this one gets opened and this one gets closed, and this one as well gets closed, and the current is allowed to pass through it to H2, and that's why it gets eliminated. Now the operator can release safely H2 push button, and this will be reflected on the operator interface as the signal lamp gets turned on. And another time, if the operator accidentally, or maybe for the reason of testing, and he or she pushes the H1 push button, there will be no effect on the other motor, since there is a kind of electrical interlock. And the only way again to stop the system is through pushing the stop push button. So now the students are asked to draw the RLC circuit, to understand it, to describe it and explain it, and to upgrade it to a PLC-based control system. So as an example here, I'm utilizing the automation toolbox I was working on, and I showed you in a previous video. Here we have the three-phase power supply, and this is the power circuit showing two induction motors, and those are the associated contactors that are responsible for starting each motor, and those are the Q1 and Q2. Those are safety components to protect the motor from the overload conditions, in case maybe the motor is stalled or the mechanical load gets heavier and the motor is loaded. So in order to protect the asset here, it is the motor against excess current values. So this overload will act as a guardian for that motor, and in case there's an excess current flowing through it, it will protect the motor, and it will open its contacts, and there will be no current passing through it to the motor, and this will be reflected onto the operator interface through the utilization of the fault lamp, which is available for the students to utilize. So one configuration in order to utilize the safety components in the circuit is appearing right here. Here we are putting both K1 and K2 normally closed contacts in series, since we don't care exactly which one will actually cause the problem, and we need to protect the circuit, and that could be associated as well with de-energizing the K2. We can rely solely on the protection provided by Q1, but it's a good practice just to support it, and by releasing the contacts of the corresponding contactor if they are already connected. So here, if we are facing any kind of overload, those will be opened and the current will never pass through it. And you can see here, this is the same circuit shown previously. Now here we add this fuse, and it serves as a protection element for the control circuit itself, and the overloads serve as guardians or protection elements in the control circuit, and their status is actually reflected onto the control logic through the terminals, both normally open and normally closed contacts appearing here in the control circuit. So whenever there is a fault case here, those one of them, since they are entitled to run one at a time, one of them will flip and gets closed, and the current is allowed to pass through it and reaches the fault lamp, and it will tell us or tell the operator whether there is a fault condition or not. Provided that the lamp is in a healthy status, that is, it is not burned out. So let's give it a try and hit the start push button and try utilizing this circuit shown here. So we need to push the start push button, as you can see here, as a response for the self-latching behavior. Now there is an alternative path, and the coil K1 gets fully energized, and the associated contacts are already flipped. So now here we are having a closed path waiting for us to push one of the two motors. Here let's start with the first motor and push H1. As you can see here, now here we have an open contact, so whenever we are trying to start the second motor, we are unable to do so, since we have a kind of electrical interlock. Now this is reflected on the operator interface, and it can be seen by the illumination of the first lamp H1, and the power contacts are already closed. So now we are hoping that the motor M1 is actually running. We cannot tell for sure, since we don't sense the current value or maybe the rotation speed of the motor. So the best we can tell so far that the running conditions are met, but we cannot tell whether there is an actual running of the motor or not, okay, until we use the appropriate sensors. Now if we would like to start motor 2 instead, we need to stop the circuit and hit start another time, and this is in accordance with a prescribed standard operating procedure. Okay, so now let's hit H2 instead, and now the second motor is running. So if we tried mistakenly, or just for the sake of testing the circuit, to hit H1 or to start the first motor, we are unable to do so. So good so far. Okay, so far so good. So now let's try examining the safety components. Hopefully you have noticed that the current drawn by the circuit is almost 7 amperes. So let's now assign a preset value for the current overload, say for motor 1, and let's now test the protection associated with the power circuit. So again, we need now to stop it, okay, and hit start another time. Okay, now we are ready. So let's start H2 first. Everything is fine. We are unable to start H1, as you can see. Now we need to stop it. Okay, now we need to start another time, and we have arranged here a fault to occur to the control logic, and we need to see how the control logic will respond to that. Now we need to start the first motor, and remember that it is presetting value is actually limiting the current passing through it, since it needs to start running about 100 ampere. This is a huge induction motor, and you can see here now this contact is actually closed, telling that the first motor has overloaded, and the associated power contact is released. And you can see here we have a kind of here we have the open contact, so there is no current passing through this branch, and as a result we are unable to start the system anymore, as you can see here. However, now the placement of the fuse still allow the current to pass through this branch and to have the lamp turned on, so that we can have a kind of feedback while operating the system. So now we need to stop the system and reset the preset value of the overload of the first motor. We need to stop the simulation. Okay, so now let's readjust the value and bring it back to 130, and now we need to change the amount of the allowed current that is passing through this fuse. We have seen that it is it requires actually about 7 amperes to run this control circuit. So now let's give it maybe 5 amperes instead. Okay, so this fuse is actually undersized. Now let's run this example another time. Okay, now once it's running, everything is fine. We can safely start the control circuit, and now we need to start the operation. So we hit this one, and now the first lamp gets on, and you can see now it draws momentarily about 7 amperes before the fuse blows out. Okay, so now since the fuse has burned out, there is no current passing through the control logic circuit. So we are unable to switch on or switch off or to do anything exactly with the power circuit, and its initial state is turned off. Okay, so this is to examine the first configuration of the RLC circuit before upgrading it to the PLC-based control system. And I told you before that this is one configuration. So what about the other configuration? It is actually shown here. Instead of putting the normally closed contacts in series before the stop push button, actually I put them in series with the corresponding motor contacts. And now once we hit start, you see now the same functionality is still applicable for both configurations. We need here to push the start and this is a self-latching behavior. Now we can safely start the first motor by pressing H1. You see now H2 is doing nothing, pressing it. So now we need to stop it and start it another time in order to start the second motor, and we need to hit H2. So everything now looks fine. Okay, so now let's examine specifically the overload. Come again to this one and put it 20 ampere instead of 130 and hit run another time. So now we are expecting the first motor to experience an overload, and this should be reflected to the control logic. Now we can safely start the circuit, and we can start motor 2 properly, since the preset value is good enough to accommodate the inrush starting current. And now whenever we are starting the first motor, we need to stop the circuit, start it another time, and now we need to start the push button to test the response. You can see here now we try to start it, but due to the overload condition, now the first overload actually tripped, and here we have a fault indication appearing on the operator console or operator interface. Now what is really interesting about this configuration is that we're still able to actually start K1 contactor. Comparing this to the first configuration, we were unable to start K1. As you can see here, we are unable to start either motor, but actually we are able to start the system. And this is actually very beneficial whenever there is another stage that can be used in order to increase the conscious of the control logic embedded within this RLC circuit. Okay, so now just to save some time, and let's move on to the real implementation, that is the realization of the previous RLC circuit using the PLC. As you can see here, this is done utilizing the Zen confirmation toolbox I showed you before, and this is the PLC, and those are the same components. Much details are available in the solution in my website, so you can visit it and have a look at that solution. Now, not much change. Actually, here I'm using the components, and basically I'm using the normally open contacts. So now I'm allowing the students here to write or to implement the control logic using MATLAB code as a beginning. As you can see here, now this is the associated MATLAB code, and let's give it a try. Okay, so we need just to start the simulation and observe the functionality of the written MATLAB code. So we need, according to the prescribed standard operating procedure, we need to fulfill the requirements of our client, so that we need first to start the system, and then we are entitled to start either motor. So, and this can be done by pressing the H1 push button, as you can see here. Now, if we try pushing H2, we are unable to start it, and this is in compliance with the requirements. So again, if we need to stop it, we need to press the stop push button. Okay, and we need to start the system another time before being able to start the second motor, as you can see here. Now, pressing H1 will actually cause nothing. Okay, so we need now to stop it. Now, to test the default behavior, now let's us assign maybe a different value for the overload. Instead of 140, just let us give it 30 for this second motor, and start the simulation another time. As you can see here, okay, we need again to start the motor, and we need now to start with H1, just to show that everything is running as expected. Now H2, pressing H2 will cause no change. Okay, so now we need to stop the system and start it over, and now we need to hit or to start the H2 so that we can test the overload condition. As you can see here we have obviously the fault lamp illuminated, and we can tell that there's a fault in one of the motors. Okay, this is the best we can tell based on one fault lamp. Okay, so now we are unable to start the system or do anything afterwards. We need to reset this fault, and this requires the maintenance engineers or technicians to come over and test the system, okay, before running it another time. So now, to test protection provided by the fuse, we can just bring this back into 140, and now we can say it's 10 just to give it 2, and hit run another time, just to test the protection and the response of the relay control logic based on that. Okay, so we can now hit the start push button. Okay, now everything is fine. Now once we try to start one of the lamps, now the fuse gets burned out, and there is no current flowing in the PLC device, and as a result we are unable to do anything with our system before replacing the fuse. As you can see here, we need to find the value for the fuse. It serves as a protection, and it should not be oversized or undersized. Okay, so the other alternative I would like to share with you here is the ability to write the control logic using the ladder diagram. Okay, so let's open it and put it side by side so that we can examine what is really happening in our system. Okay, I need to open the PLC instead. Okay, so this is our system, and this is the ladder. Okay, so we need now just to run it. Okay. Okay, there are unapplied changes. I think I need to apply it here first and then press OK. I'm sorry about this. Okay, now we can start our simulation. Okay, now we need to start the system by pressing the start push button. Now we are holding the condition. As a result, now we can choose either motor. Let's start with first motor, H1. Okay, once we hit H1, now the associated contacts or ladder will get active, and here we have an illumination in H1 and we have closed contacts here. Okay, so we need now, if we press H2, nothing will happen. We press H2, nothing will happen to the second contactor. Okay, and we need to stop it first and then restart the system by pressing the start. You need now here to observe the difference in the simulation time scale. So don't be confused with the real time and simulation time differences, okay? So since the ladder diagram is actually a little bit containing too much graphics, so it needs more time to update, okay? So here we need to push the start push button, and now we can start H2. Okay, so this is the second motor. Now it's running. As you can tell from the operator interface, here we have the second lab is actually on and the second contactor is actually closed. Okay, so now we can also test the overload conditions, maybe by presetting this value again to 20 and hit the simulation another time. Okay, now it's reinitializing. Okay, so we need first to stop it since it preserves the previous values. Okay, and now let's start it another time and test the overload condition. Okay, so now let's have it and pay close attention to the first rank. Now the first motor actually is starting, and here we are facing an overload condition, and notice the simulation time scale. Now the first output gets disabled, and the lamp here gets turned on, and the motors are protected from the overload condition. I hope this clarifies the homework for you, and do your best. Thank you.